The objective of this heat transfer project was to analyze the condenser using ANSYS software and to compare the results of heat flux to hand calculations. Condensers are used in many common applications such as refrigerators, steam power plants, and air conditioners. The project was based on the condenser in problem 11.6 in the Introduction to Heat Transfer 5th edition textbook. It reads, "A novel design for a condenser consists of a tube of thermal conductivity 200 watts per meter K with longitudinal fins snugly fitted into a larger tube. Condensing refrigerant at 45 degrees C flows axially through the inner tube, while water at a flow rate of 0.012 kilograms per second passes through the 6 channels around the inner tube. The pertinent diameters are D1 equals 10 millimeters, D2 equals 14 millimeters, and D3 equals 50 millimeters, while the fin thickness is T equals 2 millimeters. Assume that the convection coefficient associated with the condensing refrigerant is extremely large. Determine the heat removal rate per unit tube length in a section of the tube for which the water is at 15 degrees C. The geometry was created in ANSYS Design Modeler as a 3D model with 8 bodies. Dimensions from problem 11.6 were used in the analysis, and the length of the condenser is arbitrarily chosen as 15 millimeters as it does not affect the problem. The condenser was originally modeled in SOLIDWORKS and imported into ANSYS. However, the mesh quality was poor, so the geometry was modeled in ANSYS and the default mesh is shown. The mesh contains 31,265 elements and 56,814 nodes. In Design Modeler, the water and refrigerant tubes had to be modeled as solids. The solids were later specified as fluids in the mechanical application. The inlets and outlets were named as shown in order to specify which fluid is flowing where. The density, specific heat, thermal conductivity, and viscosity were specified as material properties for water in R134A. R134A was chosen because the type of refrigerant was not specified in the problem statement, and R134A is a common refrigerant. The fluid was treated as laminar flow because the Reynolds number was calculated to be 107.309, which is less than the Reynolds number of 2300 at transition. The velocity at each inlet was specified as calculated from the mass, flow rate, and material properties. Also in the mechanical application, standard earth gravity was applied and energy was turned on. The analysis types used are fluent fluid flow, transient thermal, and response surface optimization. First, a fluent fluid flow analysis was performed on the condenser. A contour of the total surface heat flux was produced as a result. The total surface heat flux ranged from negative 9.18 times 10 to the third to 1.03 times 10 to the fourth watts per meter squared. Then the geometry was copied to a transient thermal analysis. The initial temperatures were applied as thermal loads at each inlet. Convection was applied to the inside wall of the water tubes with the calculated heat transfer coefficient of 22.374 watts per meter squared K. The thermal resistance for the refrigerant was assumed to be negligible, and therefore convection was not applied to the refrigerant tube. The transient thermal analysis resulted in the total heat flux shown on the condenser. The total heat flux ranged from 1.2692 to 3.1548 times 10 to the 6 watts per meter squared. The transient thermal analysis was set to end at a time step of 100 seconds. The minimum and maximum total heat fluxes were plotted as a function of time. The heat fluxes began to level out, and therefore the solution has converged. One of the benefits of using ANSYS rather than only using hand calculations is the ability to optimize properties or dimensions. A response surface optimization analysis was performed on the condenser, transferring data from the transient thermal analysis. The input parameter was specified as the outer diameter of the refrigerant tube, as shown in red above. This diameter was chosen because a change in the diameter produces a change in the thickness of the wall between the water and the refrigerant. The output parameters were specified as the maximum and minimum total heat fluxes over time. The lower and upper bounds were set as 10.5 and 17.5 millimeters respectively, ensuring that the wall thickness will be at least a half a millimeter thick. A second-order polynomial response surface was created to show how heat flux varied with change in diameter. The goodness of fit plot shows that the points are on or close to the line of fit, and therefore the second-order polynomial is sufficient. The 2D response surface plot produced for the maximum total heat flux as a function of outer diameter of the refrigerant tube is shown. As expected, the amount of total heat flux increased as the diameter or the thickness of the wall decreased. However, after the diameter gets large enough, the heat flux gradually begins to increase. An optimization was performed using 1,000 samples to maximize the maximum total heat flux over time. The optimized maximum total heat flux was calculated to be 1.8746 times 10 to the 7th watt per meter squared, at an outer diameter of the refrigerant tube equal to 10.5 millimeters. The optimum values of total heat flux are shown on the condenser. The values of total heat flux range from 0.17184 to 1.8576 times 10 to the 7th watts per meter squared. In the optimized transient thermal analysis, the maximum values of heat flux are closer to the tube wall, whereas the maximum heat values of heat flux are more spread out on the non-optimized transient thermal analysis. To verify the results in ANSYS, hand calculations were performed. The resistance method was used with the resistance network shown. The heat flux is equal to the change in temperature divided by the total resistance. The heat flux per unit length was calculated to be 46.1541 watts per meter. Dividing by the length of 0.05 meters, the heat flux is equal to 923.082 watts per meter squared. The hand calculated heat flux falls within the range of the heat flux from the fluent fluid flow, transient thermal, and optimized transient thermal analyses. The red line on the legends show approximately where the hand calculated heat flux of 923.082 watts per meter squared falls. In the fluid flow analysis, the calculated value lies in the green region. In both the transient thermal and the optimized transient thermal analyses, the calculated value lies in the dark blue region. These colors, the green and the dark blue, are most prevalent in the respective analyses. In conclusion, the calculated heat flux from hand calculations and ANSYS analyses was approximately 923 watts per meter squared. The results from ANSYS aligned well with the hand calculations. The amount of heat flux increased as the wall thickness between the water and the refrigerant decreased. Other optimizations could be performed on different properties or lengths. Also, a static structural analysis could be performed on the condenser to determine the minimum thickness of the tube wall before the wall fells.